Hello and welcome to Virginia Aquarium. I'm Chris Witherspoon, Vice President of Science Education, and I'm here today to share with you some activities that we call water magic. And with your younger children, it's always great to start as early as you can with teaching them some early learning science skills. And the activities we're going to do today are good for your preschoolers, your kindergartners, and your early elementary students. They'll help them learn a little bit about what is science and how to conduct experiments. But of course it has to be age appropriate, so we're using water because it's something you have at home, obviously, and we know that water is very important. And we call our program Water Magic because some of the things about water seem somewhat magical, but we know it's just because of the structure and nature of water. So just to play on that, make it fun for your kids, I'm going to put my Water Magic Wizard hat on. To do some activities. We'll show you how to do the activity and materials you need. And remember, this is really important because your kids are curious, they're natural born scientists, and you can encourage that with some of the activities we're going to do today. So I'm ready and you're ready, so let's go over to our lab table and get started. So we're going to be good scientists today by starting with our observations using our senses. So let me pick up our glass of water. So we're going to take a look at our water, and our first question is, does it have a color? What does it look like? We can see that we can actually see through the water. You can see my hand behind. It doesn't appear to have what we would call a color. We'd want to know, so we've looked at it, we can smell it. It doesn't have a smell that I can detect. Does it make a noise? Listen to it. Now we know it makes a noise if we splash it around, but we're not going to make a mess like that yet. We also can feel it, so we put our hands in. It's what we call wet. We can rub it between our fingers. And we see our fingers are wet, but it doesn't really stick to our hands. And then we know that we drink water, so we can taste it. But one thing scientists always remember is you should never taste anything or even touch something that you don't know what it is in case it's something that might hurt you. But we know this is water and it's something you drink all the time. So taste would be something that you could do with our water. But let's compare that to another liquid. Actually, let me show you one other thing first. So we know that as a liquid, it pours. You can see it pour, and it goes right into this other cup. So we're going to put the water down, and I brought out one other liquid, but you could do this at home with others. This is dish soap. So we look at our dish soap, and we see that it does have a color. You can see through it, but it does look different because it's got the color. It definitely has a smell. It has some kind of scent. It's not making a noise. And this time, notice how it kind of sticks to the cup. It's a thicker liquid than the water. The water's very thin. And so we know if we stick our fingers in here, it's going to feel much slicker than this water does. And then I'm going to pour it in the cup. And look how it's a much slower pour because it's so thick. Or viscous is the word to describe that. So now we want to think about what water is made of. It's a molecule, and a molecule is made of smaller parts called atoms, and the water consists of one oxygen atom, and we're going to draw that on our paper. So we just do a big circle, and we're going to put an O in there for oxygen. And then we know that our water also has two hydrogen atoms that are part of this. We draw them over here. We'll put an H and an H. And so we're looking at a molecule, but you know, when I look at this, one way that it's easy for me to remember what water is made of is this sort of reminds me of a famous mouse that you might have seen. Does that look like a famous mouse you've seen before? So we're going to call this the famous mouse molecule, which is our water molecule, or H2O is the way scientists would say it. So we just talked about what water is. It's a molecule, H2O, two hydrogen atoms and one oxygen atom. And at room temperature, they're somewhat loosely linked together. And that's why water is a liquid at room temperature. So what we're going to do now is I'm going to pour some into my cup first, back and forth so we can see how water will flow. And now I'm going to actually pour some down on the cart. And we see it just hits and spreads out. Cart must be tipped a bit, it flowed this way. So water can't hold its shape. It only has a shape of the container it's in. So that's something else to think about, one of the characteristics of water as a liquid. But we know that water, I'm going to put these down, we know that water comes in more than one phase. So at room temperature, the phase is called a liquid. But think about what happens when it gets really, really cold. What does water do? Well, it turns into something that I'm sure you know the name of, ice. So I have a container of ice. You can see here, we've got different ice cubes. So when you get water to 32 degrees Fahrenheit in your freezer, it's going to harden up and become a solid. But we know that water can move back and forth between phases, because I want you to think about, how do we get the ice back to water? We have to warm it up, and you can do that yourself. So I'm going to take an ice cube, put it in my hand, and I'm going to squeeze. And we're going to start to see the water dripping out. Now, why is that happening? Think about it. My hand is warmer than the ice, and it's starting to melt the ice as I squeeze on it. So I'm converting the solid ice back to the liquid water. So we know how that happens, but we want to look at one other thing. We're going to look at what happens when we put ice into water. So I'm going to put the ice, I'll use our cup here, and I will drop this cube in. Not a good cube, let me put a little more water in there so you can see. If you try this at home, it's easier if you actually put some food coloring into some water and freeze it so you can really see your cubes. But look where the ice cubes are. They're on the top of the water. They're floating. And one of those magical things about water is that when you chill it and it becomes a solid, instead of the molecules getting closer and closer together, they do lock up really tight to form a solid, but they don't get all that close, so it means the ice is lighter than the water and it will float. And that's something that's different about water than some other types of liquids. So now we're going to look at the third phase of water, the gas phase, what we call water vapor. And in this little pot, I just brought the water to boiling. I'm going to take the top off and see if you see anything coming out of the pot. But if it's a little hard to see, we're going to do a way that we can maybe see it a little better. Let's look at the mirror. Do you see something on the mirror? If I run my finger around on the mirror, we caught the water vapor. Because the mirror was cooler, the steam or water vapor coming out of the pot, there was condensation where it cooled down and it became wet. You can see how I can draw on it. So when you heat water, boil water up to at least 100, it'll boil at 100 degrees, you'll start to see the water vapor coming out. Now, one thing you want to think about is that there's water vapor in you. And you're thinking, how could I have water vapor like coming out of this pot in me? Well, that's because our body has a lot of water in it. That's why we have to drink water all the time. And I'll show you a little trick with our mirror. Let me just quickly wipe it off. I can catch water vapor coming out of me. Every time you exhale, there's water vapor. And you'll see, just like the steam in the pot, I caught the water vapor on the mirror coming out of me when I was breathing. So this shows our three phases: the liquid water, the solid ice, and then the gaseous water vapor that we got from boiling. And also we know that comes out of us as well, because we have a lot of water. It's why it's important for us to always drink. And remember, if you're doing this activity, mom or dad or another adult in your house should be the one that heats up some water for you, okay? So we can be careful with that. So now we're going to do a couple activities that look like they might be magic tricks, but it really just shows us a little bit more about water and also about air and their relationship. So look at this glass. Tell me what's in this glass. Anything in this glass? Looks kind of empty to me. Let's see what you think. So what we're going to do is shove a paper towel down here in the bottom of our glass. I'm going to turn the glass upside down, and then I'm going to stick it in the water. So what I want you to do right now is think about what's your hypothesis. That means what's your question you're trying to answer. What do you think's going to happen? So I'm sticking this in, and I've got it all the way under. So now I'm going to pull it out. Oh my goodness. If you were thinking this paper towel was going to be wet, it's completely dry. Now my right hand is wet, but my left hand is dry, so I'm just shaking it out. Look at the paper towel. How could we stick that glass all the way under the water? So maybe there was something really in that glass that we didn't think about. The glass wasn't empty, it was empty of water, but think about what was in here. There was air, so we have to remember there's air all around us. And so when we turned the glass upside down and pushed it under, we trapped the air and it pushed the water, it kept the water from coming in and getting this paper towel wet. Now let's try another little test. I'm going to put the cork in. The cork floats, but let's think about, with what we just learned, how we can push that cork down in the water without actually touching it with our hands. So I've got our glass, and remember, think about what's in our glass. We've got air in the glass. So I'm going to turn the glass upside down, and I'm going to put it over the cork, and then watch what the cork does. The cork is going all the way to the bottom. You see that big bubble that came up? That meant a little bit of the air in there came out. So you see where the cork is? Now I'm going to bring it, let it back up, and I'm going to push it down one more time. And then this time, I'm going to, on purpose, tip the glass and start to let the water come out, the air come out. And tell me what you see as the air comes out. Now look at the position of the cork. It's still sitting down there on the bottom. And we start to see, do you see how the water is now coming into the glass because there's less air? And so there's more room for water to come into our glass. It's about halfway up, and I'll do one big one. And we see it's almost to the top. So we're going to do another activity or trick that shows us a little bit more about air and water when they're filling the same space. So I have a bottle, and you'll note that I have 3 holes in this bottle. So think about what you're going to expect to happen when I fill the bottle. You can see the air coming out, the water going in, and then what's going to happen when I pull it out of the water? You're going to have a mess. But I'm going to put the top on, and I have a little hole up here on the top, and I put my finger, and look what happened. The water stopped. Let me try it again. Let me take my finger off. There comes the leak. I put my finger on, it stops. Now, why is that happening? Well, this time we have the water, and we've got the air on the top, and right now it's stable, nothing's moving, but when I take my finger off, more air is coming in the hole and pushing down and pushing the water out below it, so it still goes out that hole. So if I left my finger off, that would keep going. This is showing about the pressure, the air's pushing the water down, so I can stop it again. So this is another thing. If you have an empty bottle, you can punch some holes. Another way to punch holes instead of all 3 would be to punch 1, 2, and 3, and you would see as the water goes down how the length of the water stream is different as the water moves along to the bottom. So we talked a little bit about air and water in our activity we just did, and we're going to do that a little bit here as well. So I've got a glass of water, and I have a spoon. And I want you to pay close attention as I put it back down, close attention to where the air and the water meet as I put the spoon in. So I'm going to put the spoon down, and if you look right at the spoon, right at that edge, what do you see? Does it look like the spoon is bent or broken? Why did that happen? It's because when when light passes from the air into the water, it bends a little bit because they're different substances. And to our eye, it makes the spoon look like it's bent. The same thing would happen is if we were out looking in very clear water and we saw some fish swimming around. The fish might not look bent because they're completely under the water, but where their position is would be a little bit off to our eye, would make them look like they were in a slightly different position than where they really are in the water. And that's because of how the light is coming and going from into the water and back out to our eye. So now we have shown you this and described what's happened. The word for what you're seeing is called refraction, and that's a word you'll learn in science when you get a little bit older. So now we're going to take a look at containers and how much they can hold. We call that volume. What's the volume of water they can hold? So we've got 3 containers that are different heights, different shapes, and we want to know, do they hold the same amount? Is there any connection between how tall something is, or is volume, how much something holds, more than just the height? So I have some water in here. You can take a look at how much is in this pitcher. And I'm going to first pour it into the measuring cup. And let's see, do you think it's going to overflow or just be a little bit in here? Oh, pretty much all the way up to the top. So now what do you think when I'm going to pour it into this tall one? Is it going to just be about halfway, or is it going to come close to the top? Because you know this one's much taller. Let's think about what's going to happen. Uh-oh, it's past half. It's going to be pretty much all the way up at the top. So these 2 containers so far held the same. So maybe how tall something is doesn't really tell you about the amount it's going to hold. Now let's look at this really shallow one. Do you think this is going to overflow, or is it going to hold the amount of water that's in this taller container? So we're going to take this pretty slow. We're getting close. Oh my goodness, look at this. That looked like a lot of water in that tall container, but look, this one that was very short, it's shorter and wider, it held the same volume of water. So we know that when we're looking at the amount of water, amount of a liquid, and we look at the container, just because something's tall doesn't necessarily mean that it holds more than one that's very short. Our next activity is called sink or float. And so this is a really easy type of experiment that even the youngest kids can give it a try, even in the bathtub. So if you have a selection of different types of objects, and you can ask the child, is this going to sink or is this going to float? You've already seen us do this with an ice cube and a cork. So I'm drop our cork in and we see it floats. And what we want to figure out is, why do some things float and some sink? So we're going to test a number of objects that I have up here. So let's start our test. So we already know the cork is going to float, so we'll drop that in. And now we want to start thinking about why things float. So now I've got a marble, and it's different size. Let me drop that, see what happens. Do you think it's going to sink or float? Oh, right to the bottom. So we were wondering if size has anything to do with it, but that was smaller than the cork, so we got to think about that. Got a block of wood, see what happens. Oh, it's floating. Let's try this shell. Got a shell. It's kind of a weird shape, so we got to think about, does shape have anything to do with this? Here's a wiffle ball type golf ball, so we'll put that in. And oh, it's floating, but notice it's doing something at the same. It's got holes in it, so we know some water got in there, so it didn't stay up as high as this cork. It's a paper clip. Oh, right to the bottom. About an eraser. These are all things you might have around home. Oh, right to the bottom. And then what I'm going to do is stick this cup in, see what the cup does. Oh, so look, the cup is sitting right on the bottom, but let me tip it over and let's see what happens if water starts to get in. Water gets in. It's kind of like that wiffle ball, it went under, but it's still floating. It didn't go straight to the bottom. So we kind of want to think about, why did some things go straight to the bottom? Why did some stay up high at the surface? And why are some kind of in between? So it's really not the size, it's not the weight, it's something called density. In order for something to float or to be buoyant, which is the ability to float, the object has to be less dense than the water. It has to push enough water away that it's held up by the water itself. I know that sounds a little funny, But let's take a look at this big block I have that's 12 ounces. And when I put this in, you're thinking, boy, that looks heavy. That looks like it's big, it's not gonna float. But look at it, it's right up at the top. So what we're gonna show you, I'm gonna show you is that it has to do with pushing the water away to hold itself up. Because when an object goes in the water, the water has to go somewhere. So watch when I push down with this. Watch what the water level does in the measuring cup. Wow, look how much higher it came. Look how much water that this object pushed out of the way. And that's what you need to see happening, and that's telling you that this is pushing a lot of water away because of its probably shape, and it's maybe it's got some air in it as wood. It's not as dense as something else, and it's able to float. But let's do the same experiment with something that sank to the bottom. So I've got the marble, and here's a bigger marble that I'm gonna drop in this container so you can see it went to the bottom. It's a little easier for me to hold. But what we wanna watch is, does this push any water out of the way when I push it down? You see it pushing any water? Not a whole lot. So it's kind of a test as to whether something's going to float. Does it push enough water out of the way that it holds itself up? And we drop that all the way in, and we see that it goes to the bottom. It really didn't push in because it's very dense. And that means those molecules that we talked about earlier are very tightly packed. And remember the ice we had? Grab a piece of ice. We look at the ice, and the ice is going to float because unlike other solids, when water turns to ice, those molecules stay farther apart, so it's not as dense, and it's going to actually float. Now, why did the cork floated? It's got a lot of open spaces for air to hold it up. We can push the cork down in here, and we'll see that the cork is going to actually move the water, just like it's not as big, but you can see it moving some as it goes in. It pops right back up. This other block of wood will do as I push this in, you'll see it push the water up, which tells us that it's pushing enough water away to float. So this kind of explains why our big metal ship, like a big aircraft carrier, can float. It's got to have the shape and the right density in order to push enough water away to hold itself up. So our cup here, when we filled it with water, was, and the same thing with the wiffle golf ball, they started to get water in them, and so they were, and you can see that it's now just hanging just below the surface. But when I take the water out, I've changed its density, and now it floats at the top. So activity you could do if you want to have a contest is you can get different containers that will float and see how many marbles they will hold before they sink, because you're changing its density. So I'm just kind of showing you right now. I'm just throwing some in just to give you the idea of what you could do. So you could try different kinds of dishes, and you could actually count the number of marbles it would take before you would sink it as you changed its density. So I'm going to show you one more activity here. Let me pull this out. I've got some foil. And so we know foil, it's aluminum foil, it's a metal. So we're thinking about, okay, that, you know, everything's going to float or sink. And it's not just its weight, it's not just its size, there's some other things involved. So we look at this piece of foil, and if I ask you is it going to float or sink, let's do a test. So I'm going to put it in the water this way, and it's floating right on the top, isn't it? So let me pick it up and put it in on the edge and see what it does. Uh-oh, it went down to the bottom. So this is kind of showing us that depending on which way we put this in here, then it's going to float here, and it doesn't float there. So there's a lot about design to make a boat that's going to float. So I've got two pieces of foil that are same size. So the wet one here, I'm going to do it up in a loose ball. So what do you think it's going to do? It's now it's kind of a loose ball. It's got a lot of air trapped inside. Put it on the top. Now this piece, which was the same size, instead of a loose ball, I'm going to take the foil and I'm going to fold it as tight as I can try to get it down into a tiny square. I'm squeezing it tight so remember it's the same amount of foil, same amount of foil, but we are changing its density. So I'm going really tight. So there's the same amount of foil in both that loose ball that's sitting right there at the surface of the water, and then I've taken this piece of foil and I've folded it really tight, so there's not probably much air in there. So let's see what happens when I put it in. Oh, right to the bottom. So this is just a demonstration to show, and it's something you'll learn about as you get older with buoyancy, that the ability to float is more than just how much something weighs or what its size is. It's about its density and sort of its design that would make it have the ability to float. We're getting ready to start our last activity for our session today, and this is about why some materials will absorb water and why some repel water. So we've got our container here filled with water, and we want to think about some different types of things. So if you think about something absorbing water, probably the first thing that comes to mind might be paper towels, because you've probably seen the ads on TV about being very absorbent. And we want to think about why this material might be that way. So let's tear a piece of our paper towel. And what I'm going to do is put just about 1 inch down the water. And what we want to watch is to see if the water is absorbed or moves up the paper towel. And actually, you know, if you did this with food coloring, you could really see it, but I think you'll be able to see with just the wet paper towel if you watch. Oop, it's coming up above the water level. Wow. So something you could do at home if you had different kinds of paper towels, you could test which ones are maybe more absorbent than the other by trying this test, how far up the towel it moves. You could also time how long that takes. I left one sitting like this in the water last night, and it was all the way up to here when I came in this morning. It had continued to absorb water even when I had just left it here. So you can see that this paper towel, they're made to be very absorbent. So one thing, plant materials made from plants, like cotton or the paper, actually part of their structure makes them very attractive to water. And also the paper towel is made so it's got a lot of spaces in here for the water to be able to flow into. So they're designed to absorb. But let's try another piece of paper. We'll leave this one just over here on the side so you can see. I have a piece of copy paper. In case we want to do this again, I'm going to tear this in half. So this is printer paper. And we want to see if it comes up as high. We're going to just stick it down in. We'll see if we see this one's a little bit easy because the paper's colored. And you'll see that the paper directly in the water is wet, but it doesn't seem to be sucking it up like the paper towel did. And maybe that's because this paper is made to be slicker, made for writing and copying on, and it doesn't have, even though it'll get wet, it doesn't have the spaces for the water to be sucked up into and move around into the paper. So we'll kind of lay that right there. I have a piece of foil. We've already met our aluminum foil, so we know this is a metal. So we know it'll get wet, but does it really absorb water? So I'm going to just stick the end in. We kind of stare at it. And we think that probably, most likely, that the spaces are so close together in the metal as a solid that it's wet right here. You can kind of see the line, and it didn't absorb anything up beyond that point where it was in the water. And we know that plastic also won't absorb water, and I have a plastic plate here, and if I dribble some water on it, you'll see that when you look at the plate, you'll see the water droplets just sitting there. They're not being absorbed at all into the plate. Sometimes you can kind of make them swirl around a little bit because they're just sliding along on the plate, but they're not being sucked in. If you get a paper plate, you will see them do a little bit of this if it's a coated plate that's made to not let liquid come through, but after a while they probably would get a little bit soggy. But the plastic plate is just sitting there on the top. There's not enough space for the water to start moving into the plastic. Now we've got one other fun experiment to do that we just need some setup for, and we'll be right back with you with that one. So now we've been talking about the substances or materials that either absorb or repel water. So this might be a good time for you to take a look at your rain boots or your raincoat and see what kind of materials they're made out of. So some of them are going to be a sort of a plastic type of material where you'll just see the water running off. There's some very special materials where it's not really plastic, but they make the holes in the material so tiny that raindrops can't come through so that you don't get wet on the inside. But we're going to do a little test today because I have my raincoat, and I'm going to put my raincoat on, and I'm going to let someone squirt me in the back with this. Let me put my hood on, and we're going to see if the water goes through, if this is a good raincoat, if it's going to keep me dry. So when I turn around, I'm going to get squirted. Oh, right there. Keep going. You got to really get it wet. You got to, oh yeah, I can feel that. I feel it. But we're going to see if what happens when I take my coat off with my shirt get wet. Did my shirt get wet in the back? Do you see anything? Nice and dry? So this raincoat has material that is repelling the water, keeping the water from coming through. So let's try another test. Let's try my other shirt. I'm going to put this shirt on. See, would this shirt be able to keep the water out? Would it be smart for me to go out in the rain with this shirt on? So we're going to squirt, because we're doing this in a scientific way, we're going to squirt in the same place because we want to be consistent in how we do our experiments. So right between my shoulder blades, I'm going to get squirted, and then we'll see. That's feeling a little cold. I'm betting that this water went right through this shirt because it was absorbent and the holes. Oh, my shirt wet in the back. Yep, so this material, either very attracted to water, also had holes big enough that it allowed the water to go right through onto my other shirt. So that's why you have to have the right materials if you're going to keep dry when you go out in the rain. So I hope you enjoyed our activities today, and we're going to have a guide to how to do these at home that'll be available that you can find on our website if you need more instruction, and we hope you have fun doing these on your own at home.